Okay, so today we're going to finish chapter 7 on atomic structure and periodicity. And we're going to pick it up with the Heisenberg principle, the Heisenberg uncertainty principle. Werner Heisenberg was a theoretical physicist and a mathematician in the early 20th century. I think he did a good bit of work around the time that Einstein was active also. And one of the things he devised was this uncertainty principle to try to explain why we could not locate electrons. Remember, the Bohr model of the atom said electrons circle the nucleus kind of like planets. Well, that was an unsatisfactory model. So Heisenberg's approach explained why we could not. And basically what it says was there are two factors that are considered when you're classifying any particle or any object, whatever size. One is the position. That's what X stands for. Delta X means uncertainty, like how far are you off from where it really is. That's the delta X. The other is mass times velocity, which is momentum. And if we're talking about just one type of particle or one object, then the mass becomes irrelevant because it doesn't change, but the velocity does. So you cannot know, and this delta also means there's uncertainty there. Uncertainty in momentum, uncertainty in position. And what it basically says is this is always greater than or equal to Planck's constant divided by 4 pi, which simply means that if the object is very, very large, then the uncertainty in X is very small. So something as big as I am, the uncertainty of where I am is extremely small. So you can essentially know where I am at the same time as how fast I'm moving or what my momentum is. There's Justin. Okay, I'm getting to my point. So as you shrink the size of the particle and you get smaller and smaller and smaller, then you can only know one of these with any degree of certainty. In other words, you know how fast it's going, as a consequence, its energy. But at the same time, if it's very small, then you cannot know, since this is very, very small, mass is small, then this is going to be very large in order to meet the condition here of greater than or equal to that value. So that means basically, when we're talking about electrons, since electrons are so small, you can know, if you identify where the electron is, you can't know anything about its momentum. Right? You can't know its velocity or its energy. And energy is extremely important for chemists, knowing what the energy of an electron is in relationship to the atom that it's where it's home, and in relation to other atoms where you're trying to bind them. So we essentially treat the position of the electron not as a definite place, but as a probability of finding the electron somewhere, so that we can have access to its energy. Then we just say this is a probability of where you might find it. And that seems to work best. Okay. I was looking at my own comment down here. That we've talked about Planck, Einstein. We haven't talked about de Broglie. Schrodinger comes along in a few minutes. These are some other people that were working in the, we will get to Pauling. When we start to identify and classify electrons according to their quantum numbers, just put it that way. And I'll explain what that is in a minute. Oops, wrong button. There we go. So for the wave function, Schrodinger's wave function, you may have heard of, I don't know if you have heard of Schrodinger in the past with his hypothetical cat in the box problem. You know, can you tell if the cat's alive or dead? Well, if it's in there with a decaying nuclide, and the nuclide emits a particle, and the particle is enough to kill the cat, then technically the cat can be both alive and dead at the same time. Okay, I know that doesn't mean much for us. But the wave function, this Greek letter, looks like a pitchfork, is pronounced psi. And if you have anybody that's sorority or fraternity, then they will know what that symbol means, because some fraternities, sororities use that. But in our approach here, and in Schrodinger's equations, the psi function, if it's squared, gives us an idea of the probability of finding the electron in any given point in space. Right? So if we have the nucleus here, and we say, all right, what's the probability of finding an electron there? It relates to this value. That equation tells you that value, the probability of distribution. And if you do this thousands of times for different positions, then you can develop sort of a probability three-dimensional space for where you might find that electron. That's the whole purpose of the psi function. Well, as far as we're concerned. So when you see models of atoms now with orbitals sort of drawn out in space, that's how they get it. They use the psi function to say this is the most probable location of the electron. They can't know exactly where it is, otherwise you won't have access to its energy, and the energy is more important. Okay. So if we look at the probability distribution of each of the orbitals, places that you might find an electron, they have different distributions. In other words, the distance from the nucleus on this axis says that the farther you get away from the nucleus, the less likely you are to find the electron. Doesn't mean the electron couldn't be there, but it's less likely. And this is the probability of finding it there. So at this distance from the nucleus, and that really shouldn't be that close to the nucleus. If we think this is right at the nucleus, electrons never occur at the nucleus. They're always a certain distance for the first orbital out. Right, these, who we got? Somebody must have dropped off and came back in. Oh, no, here we go. Grace. Oops, wrong pen. Okay, so we're just missing Michelle. This is a better representation here, because it says that you won't find the electron right at the nucleus. Right? Its maximum probability is at this distance for a particular orbital. And we're not too interested right now which orbital that is. We will be in a few minutes. But I haven't given you enough information to make sense of this in those terms yet. Okay. That's an understatement. it's difficult to determine precisely the orbital size. There she is. Gang's all here, virtually. And the orbital size is just a manifestation of that probability. You know roughly where the electron might be, but it's difficult to say precisely where it is exactly. And that's the purpose of the wave function, that's psi squared. So when you look at representations of an atom and the electron, I call it the electron cloud, but it's not really a cloud because there's only one electron in that space. When you look at those representations, think of them in terms of probability, not in terms of exact location. Excuse me. So for the hydrogen 1s orbital, and I'll explain what that means in just a minute. That's the only orbital but that's the ground state, we call it. In other words, at room temperature and pressure, the hydrogen atom will have an electron and it'll be at the ground state. And this is the lowest possible energy for that electron is in the 1s orbital. And the radius of that orbital encloses about 90% of the total electron probability. So we have to, at this level, the quantum mechanical level of an atom, we have to speak in terms of probability because there's no way we can know exactly where things are. All right, so how do we define these orbitals? Well, there are a set of equations and they derive from Schrodinger's equations. And there are four numbers. N, L, M sub L, and M sub S. These four numbers are unique for each electron in an atom. And no two electrons can have these same numbers here. All right, what do they mean? Well, the first one, well, in general, these, when inserted in the equations, they give you a probability of energy and probability of distribution of an electron around an atom. Okay? Think of them also as nested numbers. When you have a number for this one, then this one is based upon what that one is. And the allowable numbers here are nested in that number. And this one is nested in this number, whatever it happens to be. This one is nested in that number. So they can bloom. You can only have, well, you can have any number, but they're all integers here. 1, 2, 3, up to, well, that's a poor choice. Up to, well, any number. But they're always whole numbers starting with 1. Okay, this is called the principal quantum number. And it tells you roughly the size of the orbital, and it tells you roughly the energy of the orbital. So any electron with this number as its first, if they both have this number, then they will be similar in energy. They won't be exactly the same, but they'll be similar. And this one actually derives from Bohr. Remember Bohr's model had, let's see. Yeah, it had an N in it. And it's always a whole number. Okay, so the principal quantum number refers to size and energy. So this one will be bigger than that one, and this one will be bigger than that one, and so forth. And this one will be higher energy than that one, higher energy than this one. So you can see them expanding away from the nucleus, which means more energy. Right? Remember, an electron that's close to the nucleus is low energy. If you want it to move to a higher level, more energy, you have to put energy into it, and then it jumps out. So that's why the further from the nucleus, the more energy the electron has. Okay, this one is the azimuthal, which is kind of hard to say. Angular momentum is easier to manage. The angular momentum quantum number is L, and it defines the shape of the orbital. Sometimes this is called the subshell. Some books will call this the shell and this the subshell. And then they would call this one the orbital. So you might see it this way in some books: shell, subshell. I don't think our book does. And this is called an orbital. So I've been using orbital sort of as a catch-all for everything. But you will probably see them used this way: shell, subshell, orbital. This one, the angular momentum, has to do with the shape. So is it generally spherical in shape? The probability of finding an electron will be in a spherical location. And it doesn't have to be spherical in terms of a solid ball. It can be spherical in terms of a shell around the electron. These numbers are based upon these numbers. So they can go from, using X, they can go from negative X to positive X and any whole number in between. So this would be, let's see. Well, let's say if we start with 3, it would be -3 is possible, -2, -1, 0, +1, +2, and +3. That's what I'm trying to get at. So if you have an n equals 3, then you can have a possible number of L subshells at that level of 1, 2, 3, 4, 5, 6, 7. Okay. So if we just have 1, then what are your options? Well, you can go -1, 0, +1. That's it. Okay, let me move this down some. M sub L. That's the angular momentum number. The magnetic quantum number gives you information about the orientation of the orbital. If it's spherical, then the orientation is just what it is, right? You can't be oriented in a different way if it's round. But if it happens to be sort of a dumbbell shape, it might be pointing that way, it might be pointing this way, or maybe it might be pointing that way. Possibilities. And then there are other shapes that are available. But it defines the orientation in space, M sub L. M sub L is based upon L. So if we have, let's see. Oh, wait a minute. I'm sorry. I confused myself. Hope you're not writing me. I'm getting ahead of myself. This one is 0, 1, 2, up to x minus 1. So 3 would be 0, 1, and 2 possibilities. Okay, I'll give y'all time to erase and change your notes. If I just pay attention to my slide, I would have caught that right away. This one is based upon these. And now this one is minus L up to plus L. So if it was 2, then it would be -2, -1, 0, +1, +2. Okay. And this refers to orientation. And then the last one is the spin quantum number, electron spin. Think of an electron as a top. It can either be spinning this way or this way. That's the only option. So this number is either plus 1/2 or minus 1/2. Whatever it is inside here in any one of these, then it's plus 1/2 or minus 1/2. So what that says is, if you have an electron with this spin, and you have another electron with that spin, then you can have these two inside that orbital, or you can have two maximum inside this one, or two maximum inside that one. All right, so this came straight out of your book. It just tells you how many orbitals at this level you can have for each n. All right, so let's take this one, 3. So you can have 1, 2, 3. So you can have 3 possibles at that level. And then each one of these, this one can only have 1, right? Because minus 0 and plus 0, it's only 1. Let's see, let's do it this way. Plus. And then at this level, you can have 3, minus 1, 0, plus 1. So there's 3 possibilities. And at this level, you can have minus 2, minus 1, 0, plus 1, plus 2 is 5. Okay? So how many orbitals does that mean? Well, total at this level, let's see, at this level is 9. Okay? 5 plus 3 plus 1 is 9. 9 maximum for, oh, wait a minute, I'm sorry. Where are we going from? We're going from here, aren't we? 2. Oh, okay. It's not going far enough. I was going from 3. That's right, from 3. Yeah, that's right. That's right. 9. 9 possible at this level. So you can see how it kind of cascades. So let's take what we know and see if we can see if any of it has sunk in. For principal quantum level n equals 3, determine the number of allowed subshells, different values of L for 3. Right, we did that already. So if we have 3, you can have 0, 1, and 2. Right, 3. 1, 2, 3. And L can either be 0, or it can be 1, or it can be 2. But here, 0, 1, or 2. Now, when we start writing electronic configurations, like putting electrons into the atom from low energy to high energy, as you add more protons and build your atoms, then you add electrons in and they go in at the next available energy level. You start from low and go to high. Well, it can get kind of confusing if you only use numbers, like 3-2- something. So what we do is we give these letters. The 0 subshell is an s orbital. Right? It has a particular shape. The 1 orbital is a p, and it has a particular shape. And the one with quantum number 2 for L is D. And then if we go to 3, that'll be an F. And those are all the ones that we're going to need for the existing elements on the periodic table. S, P, D, and F. So what we're saying here is this is n equals 3, and then this is L equals 0. N equals 3, L equals 1, N equals 3, L equals 2. That's what those letters stand for. And that avoids confusion when we start writing out, particularly in shorthand, writing out the electronic configuration of an atom. Now you may be wondering, why do we want to do that? Well, the electronic configuration of an atom informs you about its chemical behavior, how it's going to react. Okay, for L equals 2, what are the magnetic quantum numbers? So L equals 2 now, this one. What are the magnetic quantum numbers? Well, -2, -1, 0, +1, and +2. Just like that. So the number of orbitals is 5. And while we're here, how many electrons can we have for each of those numbers? We can have 2. You can have a +½ -½ for each one of these. So that means if this is equal to 2, the D, you can have a maximum of 10 electrons in that particular subshell. Something in your eye. You have drops. Do you need them?
I'll be okay.
Okay. All right. So this looks like the orbital shapes. So what we're looking at is the L level, right? This is energy and size. This is shape. So the S orbitals are spherical in shape. And we have different representations for them. This is what they would look like from the outside if they were solid spheres. It wouldn't tell you anything about the inside, but if we slice through it, then we'd see differences here. The 1s orbital is almost solid. The 2s orbital, though, is the same shape, but it's a different size because it's a 2 and not a 1. Notice we have a node in here. So what's a node? A node is a place, a region, where the probability of finding the electron is 0. Right, so n equals 2, you have 1 node. N equals 3, you have 2 nodes. N equals 4, you'd have 3 nodes. N equals 5, you'd have 4 nodes. But they're all spherical. And if we looked at them as a Cartesian graph, we would find that it roughly goes like this, only, like I said before, the probability of finding it at the nucleus is 0. So there really should be a kind of an extreme dip here to 0. The 2s orbital, there's your node. And you have most of the probability is very high, close to the nucleus, but you have a significant contribution of probability further from the nucleus. Same with the 3. You have probability here and you have probability here with these nodes. The p orbitals, we're down to this level, p orbital shape, right? These are spherical. These are kind of dumbbell shaped. And you can have 3 possibilities. They can be oriented on the x-axis, the y-axis, or the z-axis. And that refers to this level. This is orientation in space. So for this one, 1, you have a possibility of -1, 0, +1. And it's convenient to think of this one as maybe orientation on the x-axis, the y-axis, and the z-axis. And the orientation here also gives us some information as to how an atom is going to react when it approaches another atom, right? Because bonding occurs with overlapping orbitals. So if you've got this atom approaching some other atom and their orbitals don't overlap, then it's less probable that they're going to form a bond. They have to be oriented correctly. All right, you get some really wild. Now we're up to the d orbitals, right? You can have 5, 1, 2, 3, 4, 5 from the d's, and these are the shapes. And actually the shapes are here, and these are the orientations. So the shapes can range. They're kind of a double dumbbells. Double dumbbell, double dumbbell, double dumbbell. And then you got this last one with a dumbbell and a donut. So and these are, nobody has actually seen these. Right? These are all calculated from Schrodinger's equations. And then F gets even wilder, right? And F can have -3, -2, -1, 0, +1, +2, +3. So it can have 7. And that's what you see here. 3 + 4, 7. Okay. You're not going to have to draw those things, right? I'm just illustrating what they look like. If anything, I would note that this one is spherical and these are dumbbells oriented on 3 axes. And that's as far as we need to go in this course. Okay, electron spin. These are the electron spin quantum numbers, +1/2, -1/2. And they are these values because that's the way they go into the equation and give us the probabilities that we're looking for. I mean, this is not just accidental creations. That's what they have to be, either +1/2 or -1/2 to satisfy the equations. Okay, so let's get some of the rules that help us understand how to use these numbers. First one is the Pauli exclusion principle. Right? We saw Pauli's name earlier on a previous slide. His exclusion principle simply states, actually, I've said it before, no 2 electrons can have the same set of quantum numbers. So they can have the same 3, right? They can have the same 2. They can have the same +1. But if they do, then they have to have a +1/2 or a -1/2. Okay? They have to have unique sets of quantum numbers. That's the Pauli exclusion principle. This stuff works fine for the hydrogen atom. So we got 1 electron. The problem arises when you start to get more electrons in there at once, which is the rest of the periodic table. These polyelectronic atoms present, if nothing else, they present repulsions. Because when you try to pack electrons into a similar space, then they're all negatives, they're going to repel one another. And that changes the energy level structure of atoms. And that's an important consideration when you're looking at, drawing the electronic configuration and assessing how one atom reacts to another. We can't calculate these exactly because we don't know where they are. Right? We can only estimate the change in energy levels that polyelectronics impose on their atoms. So these might say that your energy level is 2, but when you get 2, 3, 4, 5, 6 electrons in that neighborhood, then they cause these others to shift. And I'll illustrate that in a few minutes if I don't waste all my time talking. So when we start adding protons and building successive elements, then we have to add the electrons to go with them because they're neutral in the beginning. They go in lowest energy first. So we start with the hydrogen atom, that electron goes in the 1s orbital. Subshell. And then you can build helium. Well, helium has 2 protons, but there's room, right? 0, 0. There's room for 2 electrons there. So there's room for helium at the 1s level. And they go in, the electrons go in next highest energy level. So the first guy there gets to sleep on the bottom bunk, and the next guy has to go to the second bunk. And then the next one has to go to the third bunk. And then, well, actually, that wouldn't be right because you go to a different set because there are only 2 bunks available for you. All right. So this is a screenshot of a flash video that's no longer supported, but the the picture tells us something about how the energy levels shift. We would expect to see the 3s, 3p, and 3d at exactly the same energy level because they're all threes. But what happens is they interact in such a way that the energy level of P gets shifted up. The energy level of D gets shifted up. So the P is shifted up here. So they're in the general region, but they're not exactly the same. So the s orbitals are lower energy than the p orbitals at the same principal quantum number. And those even shift as you start to build bigger and bigger atoms. Okay. So let's talk about the penetration effect. Remember the diagram where we had the 1s orbital kind of went like, I think it should go like this. That. And then the 2s orbital was more like this, and then it went to a node, and then it went out like that. And then the 3s orbital was more like this, and then this, and then this. Right, it has two nodes. Well, the penetration effect says and this is just for the s orbitals. If you look at the p orbitals, they have a different profile, but when you look at their electron distribution probabilities, then you see that some of the p orbitals have a higher probability of finding the electron closer than the s orbital. That's the idea of penetration. Wherever you find significant density of electrons underneath another one, you're saying it penetrates below the higher energy level. So what we're saying is that the 2s orbital is lower in energy than the 2p orbital in a polyelectronic atom. And we saw that in the previous slide. Right here. Yeah, 2s is less than 2p. Right here, so 2s is less than 2p. The 2s penetrates closer to the nucleus, so it's lower energy. Okay, here's another, and this is another representation. If we look at the 2s, the 2p orbital only has this one distribution. But the 2s orbital has this, okay, I'll take their word for it. It says that most of the 2s density is out here beyond the 2p, but there's a significant, after it reaches the node, there's a significant amount closer to the nucleus. That's what keeps the 2s overall energy lower than the 2p because of that penetration effect. Right? And for higher orbitals, you can see more nodes. And if you compare all the three level, right? The 3s is going to be out here with two nodes. The 3p is going to have one node, but it penetrates below the 3s and the 3d. But you still have some significance here. So without twisting myself into knots, let's go back and look at this. Even though you get significant density of the d orbital, of the s orbital beyond the p's and the d's, you still get significant penetration of the s, so that its overall energy is less than the p's and less than the d's. That's the penetration effect in a nutshell. Okay. Now, before we start drawing the electronic configurations for atoms, let's do a little history with a periodic table. So since I can't get the periodic table on this screen, it's over there. It might be well for you to pull out your copy. There will be copies thrown up here, but maybe this doesn't come through very well, and a copy right in front of it would help. Periodic table. Okay. Historically speaking, chemists were noticing by the mid to late 18th century that there were physical and chemical characteristics of certain elements that they noticed were similar. And the first person, Johann Dobereiner, grouped these into triads. He noticed that chlorine, bromine, and iodine had very similar behaviors, chemical behaviors. And those are all halogens. So we know from experience that, well, he was right. They do have similar behaviors. They're not exactly the same, right? They're just in the same family. Well, that's as far as he went. He grouped several, he created several triads from the available chemical data. And almost simultaneously, another German, Julius Lothar Meyer and Dmitri Ivanovich Mendeleev, who was, you may recognize that name, they both conceived of a periodic arrangement of elements, almost at the same time. The difference between the two is, well, what do we mean by periodic arrangement, right? Have I described that before? If you follow the way the periodic table is constructed, you have groups, families of elements like this, right? They have similar characteristics. But if you go from left to right, and you say, okay, this one, these all have the same characteristics, you go to the next one, they have different characteristics, and you're going across. These are groups or families, these are periods. If you go across, then you find that they're changing characteristics all the way across. And then when you get to the noble gases, then if you say, all right, so the next proton that I add, I've got a group element out here. Wait a minute. It behaves like this one over here, right? So you loop around and start a new period. It's like periodic motion. You know what periodic motion is? Think of a grandfather clock with a swinging pendulum, right? Periodic motion is motion that goes through a cycle and comes back to where it started. So we're going through a cycle and we're coming back over here. Going through another cycle and come back over here. That's a period. And the period is dictated by these similar characteristics. So that's why the periodic table doesn't just string out one long list from left to right. We wrap back around and put these in the same family where they're supposed to be. Well, the difference between Meyer and Mendeleev, even though they both conceived of a periodic arrangement of elements, what Mendeleev did was he took this table and he arranged the elements according to not just chemical characteristics, but physical properties and atomic weights, the weights that they knew at the time. And what he did was, if he came along and said, okay, the next one is supposed to be here, but it ought to be in this family, right? It shouldn't be over here, it should be there. But there's an empty spot now because he skipped over this one and went to that one. And he said, okay, I had to skip this one because that next one that we know, right? They didn't know all the elements. The next one that they know needed to go in that family. And he said, okay, this one is going to have these characteristics, and it's going to be approximately this weight, among other things. And he did that for several elements. And he made a prediction, said, this is what's going to be in that spot once we find it. Sure enough, we found them all. That's why Mendeleev is given credit for the periodic table, because he used it to predict the existence of undiscovered elements. And in fact, part of the reason he was successful, and he admits this in his published letters, well, letters that we know about now, was that he used the work of Cannizzaro. Remember, Cannizzaro was a student of Avogadro. And Avogadro's work and Cannizzaro's publications allowed chemists to determine the true molar mass of an element. And Mendeleev gave Cannizzaro credit for helping him construct his table so that he could get things in the right place and predict their weights. Okay, I spent enough time on that. The periodic table is arranged by families vertically and periods left to right. And some of those families have names, right? And if you've done the extra credit on constructing the periodic table, you know some of those already. Like the alkaline metals are the first group, alkaline earths the second group. These are all transition elements. Then you have halogens and noble gases. This one would be let's see, 7, 6. These would be the chalcogens, oxygen group. This would be the pnictogens, the nitrogen group. Then the lanthanides and the actinides. So that sort of gives us some orientation, general orientation. And this leaves out the dividing line between metals and nonmetals. Follows that line right there. Yeah, there it is. Notice that these elements right here are on the dividing line between metals and nonmetals. Those are metalloids. Depending on the environment, sometimes they act like metals and sometimes they act like nonmetals. That's why they're called metalloids. And these actually form the foundation for our semiconductor industry because they can go both ways. And we select how they behave in our microchips. Okay. So now we're going to get to constructing the electronic configuration of a neutral atom. And we follow what's called the Aufbau principle. That's a German word. I don't know what the German word means. I just think of it as Aufbau principle means this is how you do it. Basically, as you add protons to build the next successive elements, you have to add electrons, and the electrons go in order of energy. That's the basic principle. So when we take an element, in this case oxygen, right? We know that oxygen is going to have 8 protons, which means it has 8 electrons in the neutral atom. Right? So if a quantum number 1 can have how many subshells? Right? -1, 0. That's it. It can only have that. And this is an S. So 1s is the only possibility for the first energy level. And then for the next one, n equals 2, we can have what? Well, we can have 0 and 1, right? This is 2, then we can have 0 and 1. That's S and that's P. So we can have 2s and we can also have 2p. Next energy up. Okay. We could keep going. We could have 3. 3s can have 0, 1, and 2. So the 0 and the 1 and the 2. Okay, that's why they're in that order. Now, as you get higher and higher, we're going to find a place where we get some switches. Right? And I'm going to show you how to deal with those in a minute. But for oxygen, how many can we have in this orbital? Right? We're down to the S. What's next? The M, the M sub L. Let's see, L, M sub L, and then below that is
Yeah. This is N, this is L, and then the M sub L, this one can't have one because it's only 0. But this one could have, right, if this is 0, then it can only have -0, 0, and +0. It can only have 1. Right? But this one can have -1, 0, and +1. Right? So this one could have 3. Right? And sometimes we call those X, Y, and Z because of their orientation. But this refers to -1, 0, and +1 as the M sub L. Okay, so what that means is you can have a maximum of 2 electrons here. That's it, -1, +1. 2 electrons here. But you can have 2, 4, 6 at this level. So P could be a maximum of 6. Right? But do we need that many? 6, 7, 8, 9, 10. No, we don't need that many. We only need 4. Okay, so we've used up all the electrons in just this section right here, just like that says. Right. So we're going to cover it in a minute, but I'm going to go ahead since we've got the diagram up here. How do they go in here? If you're going to put 4 electrons in there, how do they go in? Well, they can either be M sub L, they can be M sub S +1 half or -1 half. And I usually say this is spin up and this is spin down. That's the way I represent it. So in here we can go that 1, 2, 3, 4. That means that you put all the spin ups in first. And then if you have any left over, you can go back and pair them up. But they always occur separate from one another in these subshells until you get them filled up, and then you go back and finish putting them in. Okay, so that covers oxygen. And shorthand is just to write it that way. Okay, what I just showed you was Hund's rule. Okay, where you do this like that. 1, 2, 3, 4. Hund's rule says you have to have the maximum number of unpaired electrons before you can start pairing within a subshell. And that's simply, you can think of it as if they're in separate shells, then they're not as likely to repel one another. So if you keep them separate until you have to put them together, then you get some repulsion in here, but you get less over here. All right, that's Hund's rule. So we've got Pauli exclusion principle, we've got the Aufbau principle, we've got Hund's rule to govern how we build an atom. The creators of the slides like these up and down there, so that's too much trouble. I just draw a line and put a half bar. So there's oxygen. That's known as the orbital diagram. This is the orbital diagram format. This is the shorthand electronic configuration of the atom. Now, what is the valence electron? In short, the valence electron is any electron that is available for bonding. And the electrons that are available for bonding are in the highest energy level, the highest principal quantum number. So any 2s, in this case, any 2s will be valence. So we have 2 plus 6 is 8. We have 8 valence electrons. And if you look at the old style, that periodic table doesn't have it. Old style periodic tables have alkaline metals are Roman numeral 1A. Alkaline earths are 2A. The aluminum groups are 3A. Boron, excuse me. Boron group is 3A. And then the carbon group is 4A. and on across. These Roman numerals tell you how many valence electrons are in the members of that group. That's why it would be nice if we keep both the new system from 1 to 18 and the Roman numeral system on the same chart. And some of them still do, because it's useful to tell you how many valence electrons there are. Okay. Now, this is an extremely important idea to consider. When you're looking at a periodic table, the orbitals that are currently being filled for the alkaline metal group and the alkaline earth group, the s orbitals are the highest energy levels being filled. That means they'll be out here on the right, and the alkaline metals will only have 1 electron in them. The alkaline earths will have 2 electrons. So that s orbital would be filled with the alkaline earths right here. Then if you go follow the period across, you start to fill the p orbitals, right? So this would be a 2s, this will be a 2p. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 gives you noble gases. And if you know the structure of the periodic table, it's easier to write the electronic configuration for any atom because you know which ones are being filled and what their numbers are. If we stay on this period, say 4s, 4p. Notice that when we get into the transition metals, we're filling d orbitals. And when you fill a d orbital on this period, you drop down 1 principal quantum number. And what that says is, this is the lowest energy, then this is the next lowest, then the 3d1 is the next lowest, not the 4p1, 3d1. And I think I've got a slide in here. Yeah, it's coming up. That gives you an alternate way of knowing which ones come in which order as you draw the electronic configuration. And when you get to the lanthanides and the actinides, you're filling f orbitals. Okay. This is one way to do it. If you don't have the periodic table available, or if you just prefer this method, if you write the orbitals, this is the 1 level, it only has s. The 2 level has s's and p's. 3 level has 3s, 3p, 3ds, 4s, 4p, 4d, 4f. And you just keep going down. And you draw diagonals. Right? So you fill that one. Then you go back over here and you fill this one. Then you go back over here and you fill this one like that. Then you fill this one like that. Then you fill that one like that. So you'll notice that they're in expected order as long as you do 1s, 2s, 2p, 3s, 3p, 4s. When you get past 4s, then you go to 3d, not 4p. And then you go down to 4p and 5s. And then you go back up to 4d, 5p, 6s. That. Okay? So that's one way around getting confused. All right, so let's take these examples. How much time do I have left? I should have used up some of the lab time last time, got us further along. That way I wouldn't be rushed. Okay, so sulfur. How are we going to do sulfur? Well, find out how many protons it's got, which means how many electrons. And sulfur is 16. Okay, so 1s, 2s, 2p, 3s, 3p. D, No, 4s. 4s, then 3d.
Yeah, 1, 2, 3, 4. That's right.
In energy order. Now, we may not need all those. So how many we put in here? 2. 2 in that S, 6 in that P. All right, so that's 6, 7, 8, 9, 10. So we got 6 more, 2 more, and 4. And that's sulfur. Okay. Now, another way to write this, if you're only interested in the valence electrons, and you have a bigger atom, then look at what happens if you start from here and you go backwards through the period, and you get to here. Once you get to this one, that's the same electronic structure as neon. So if you write neon in brackets, and then write 3s2, 3p4, that's sulfur. Okay, if you don't need to know that, or if the question says use the abbreviated shorthand, or if you're only interested in the valence electrons, then this is a good way to write it. Saves you a lot of trouble. But you can only do that if you know how the periodic table is arranged. And if you take the periodic table and you say 16, then you say, all right, there's sulfur 16, and back up, and you back up to neon. Neon uses up 10 of them. Well, okay, sulfur is in the third period. So if you go from left to right, you go 3s2 and then 3p4 to get to sulfur. That's a good way to do barium, because barium is huge. Right? If we had to write barium out on this short board, I'd have to wrap it around. But since we know barium and where it's located on the periodic table, then if we take barium and go backwards, we get to xenon. And xenon, let's say barium, is 56, but xenon is 54. All right, so when you go from xenon down to the next period, where are you located? Where do you count your periods? Hydrogen, lithium, sodium, potassium, rubidium, cesium. That period is 6. And we know that 6s is being filled from cesium to barium. Cesium would be 1, barium is 2. So that's why we can say this, and that's barium. And we know that we only have 2 valence electrons in barium. That's why for all of the alkaline earths, when they form ionic compounds, they lose those 2 electrons so that they can look like xenon. Or strontium would look like krypton, or calcium would look like argon, or magnesium would look like neon. When they lose those 2 electrons, they have the same number of electrons as the noble gas that's back 2 from them. That's known as they're isoelectronic with those noble gases. And that's where they want to be. Okay, europium is a little weirder. Let's see, where is it located? Europium. Oh, it's a lanthanide with 63. Okay, so if we take europium and back up, europium would go back to samarium, promethium, neodymium. Protactinium, cerium, and then we get to lanthanum and barium, cesium, and then xenon. So we would go to xenon here also. But that leaves us 9 more electrons. We have to do something with those 9 electrons. And those 9 electrons are 6s2 and then 4 F7.
Notice that when you're in the lanthanides, you're on the 6th period. But if you get over into the Ds, excuse me. When you get over into the Ds, for lanthanum, you're into the 5Ds. But when you get to the lanthanide series, you back up even one more, 4 Fs. And that's based upon that diagonal diagram also. Okay. All right. I'm unlikely, it's unlikely that I'm going to throw any of these Fs at you. We'll just stick with the SPs and Ds. Because things can get kind of squirrely down there in the Fs. Your expected electronic configuration may not be the one that is true, based upon the rules that I've given you so far. Now, if we're good, we do get some odd switches, anomalies, we might call them, in the transition metals. But I'll point those out when we get to them. Okay, periodic trends. We got 5 minutes. Okay, I'm going to go over, so if you have to leave, fine. Periodic trends on the table. So we're looking at the periodic table. We want to answer some questions about these factors: ionization energy, electron affinity, and atomic radius. Now I need to define what those are, of course. The ionization energy is the amount of energy required in joules or kilojoules, whichever the case may be, to remove one electron from the atom or the ion. So if it's first ionization energy, you're starting with a neutral atom, and you end up with a positively charged ion and 1 free electron. That's the amount of energy per mole of magnesium that it takes to accomplish that, 735 kilojoules. Okay. Now, if you take this one, this ion, and you kick off another electron, it takes more energy. And if you take that one and kick off another electron, it takes even more energy. And what we're seeing there is an electrostatic effect. When you're removing this electron from a neutral atom, it's a lot easier than if you've already got a positive charge and you're trying to pull another electron away from it. So it takes more energy. These are valence electrons, the first and second for magnesium, because it's an alkaline metal, an alkaline earth metal. But when you get down into this third electron, you're into what we call the core. In other words, these are valences, right? Their magnesium is, that's 3s, right? You've got 2p and 3s2. I'm not going to write the rest of it for magnesium. So the first ionization energy and the second ionization energy are at this energy level, that distance from the electron. Now, when you come back to the P's, you're closer to the nucleus. Right? These are core electrons, and it takes a lot more energy, 5 to 10 times as much energy to remove an electron from the core as it does from the valence. Okay. That explains ionization energy. And when we write ionization energy, it has to be a gas going to a gas plus the electron. Now, why does this have to be a gas? We know magnesium is a solid at room temperature and pressure. But in order to judge the removal of an electron, you have to get it in the gaseous state. Why? Because the energy you put in may be consumed in the beginning in converting a solid into a liquid and a liquid into a gas. And then that doesn't tell you anything about the energy to remove the electron. So you have to get it into a gas first, no matter what its normal state. It has to be a gas first. Then you can judge the amount of energy required to move that electron. Okay. Okay, as in general, as we go across the period from left to right, the first ionization energies increase. So magnesium is going to have a first ionization energy that's greater than sodium. And aluminum is going to have a higher first ionization energy than magnesium, and so forth, on across. Now, why is that? You're at the same principal quantum level, 3s and 3p's. So you're not really moving out or closer to the nucleus. So the only explanation that makes sense is you're adding more protons. You've got more protons pulling on those electrons. It takes more energy to remove the first electron. That's known as increasing nuclear charge caused by the added protons. That explains the first ionization energy trend from left to right. Now, what about up and down? As you go from top to bottom, the first ionization energy decreases. Okay. As you're going down in a family, what's happening? Well, you're increasing the principal quantum number for the next layer of electrons out on the outside. They're at higher energy levels, so it takes less energy to move them from wherever they are to infinity, right? So the electrons being removed are farther from the nucleus, and the energy that would normally be holding those electrons in by the protons is being shielded by the core electrons. The core electrons are sort of soaking up the attractive force of the protons in the nucleus. So these electrons out here are not feeling the pull quite as much. That makes them, as you move down the family, takes less energy. So what does that mean? That means if you go up, you're increasing. So go up and to the right, you increase the first ionization energy. So the trend is lower left to upper right is increasing first ionization energy. All right, so this just illustrates left to right through a period, lithium, beryllium, all up to neon. So the general trend is increasing in this period, and this period, and this period, and this period. You'll notice some anomalies in here. Beryllium to boron, nitrogen to oxygen, magnesium, aluminum, phosphorus to sulfur. Those anomalies, this is physical evidence. We have to explain why. And let me see, is that part of my slide? Maybe not. Oh, yeah, it does. So we're going to talk about it on this slide. Why is that trend not linear? Why do we have some of those dips back up? The major factor is electron repulsion. In other words, as you get more electrons, they tend to start repelling each other. And you go across, say, on the second period from lithium, beryllium, boron, carbon, nitrogen. And we go from nitrogen to oxygen. So nitrogen to oxygen would be 7 to 8. This would be 1s2, 2s2, 2p, 3. 3. And this would be 1s2, 2s2, 2p, 4. So this is the same, this is the same here. The difference is in the p orbitals. So in this one, we have 3 levels, right? This one we have 3 levels. How do the electrons go in? We go like that, like that, like that. Like that, like that. Oops. That, and then like that. So when we say electron repulsion, we're talking about at the subshell level, the orbital level, excuse me, orbital level. These are unpaired.
right? So they experience a certain repulsion, but these are paired, and the repulsion here is great enough to reduce the amount of energy required to remove that one electron. This is the electron that will be removed for ionization. And the repulsion there makes it lower here. So instead of going like this to nitrogen, then it drops down to oxygen before it goes back up. Okay. That's what they mean by other exceptions from beryllium to boron. Okay, for beryllium to boron, beryllium is an s orbital at this level, and boron is p orbital at that level. For that one, it's not so much repulsion as it is the p is at a higher energy level, so it takes less energy to get it to infinity. Right. For this one, yes, electron repulsion. Beryllium to boron is a difference in energy levels for the electrons. All right. So, which one of these atoms would require more energy to remove an electron? Sodium or chlorine? Well, let's see. Are they in the same period? Yep. So all we have to do is look at the trend. Sodium is on the far left of that period. Chlorine is on the far right. So chlorine takes more energy. Oops. Because it has more protons. How about this one? Which would require more energy to remove? Lithium and cesium. They're both alkali metals. Cesium's toward the bottom, lithium's toward the top. So lithium would take more energy to remove its first electron than cesium would because of the vertical trend. Cesium's lower. Its first electron to be removed is at a much higher energy level to start with, plus it's shielded by core electrons. So that would take more energy. How about second ionization energy, lithium or beryllium? Well, lithium is 3 and beryllium is 4. Right? So we're talking about which electrons are going to be removed. This one is 2s1 and this one is, oh, excuse me, 3s1. No, I was right. 2s1. So it's 1s2, 2s1, and this is 1s2, 2s2. Okay, how about the second ionization energy? Well, if we make an ion out of it like that, that means this one's gone, and this one's reduced to 1. Okay? So, we're not down in the core yet for this one. So it would take more energy, but not much more, or maybe twice as much. But this one, you're down in the core. So this one would take a lot more energy for the second ionization than beryllium would. Okay. All right. And this chart came straight out of your book. It just makes the point at where the breaking line is between valence electrons and core electrons. So you notice that here between these two, you get a huge jump because when you go into ionization, second ionization for sodium would be core. Third ionization for magnesium would be core. Fourth ionization for aluminum would be core, and so forth. Okay, what do we mean by electron affinity? Ionization starts with a neutral atom. Electron affinity also starts with a neutral atom. So electron affinity is not the opposite of ionization. It's a separate concept. So you're starting with the same neutral atom. Only now, instead of putting the electron on that side, you put it on this side. Okay? So what are we doing? We're adding an electron to a neutral atom to make a negative ion, an anion. How much energy do you get back from this? Okay.
As we go across a period from left to right, the electron affinities become more negative. So think of that in terms of the system. So if you get a system and the electron affinities, the energy is negative, that is, energy is being released as the electron is added to. So the more negative the electronic affinity, the more attractive the electron is to the atom. Okay, that's a difficult concept, I know. It helps if you think of it in terms of system surroundings. So the more negative the value, the stronger the attraction of the electron for that neutral atom. Okay, now we can say, what's the trend? The electron affinities become more negative as you move from left to right. And they become more positive as you go down a group. So they become more negative as you go up the group. So if we think of those in terms of strength of attraction, then the strength of attraction for electron affinities is from lower left to upper right. Oops. No more explanation for that? Why is that? Well, from left to right, it's the same reason. You got more protons at a given energy level. So more protons attract more strongly any external electrons. Okay, as you go down, then you have more protons, but they're shielded by core electrons. So there's not as strong an attraction. That's why down, the value becomes more positive. If you go up, it becomes more negative because you have less shielding on the protons and they attract the electrons more strongly. So similar reasons for either ionization or electron affinity. Oops, we're going way past. Okay, if you got to go, go. I'll keep talking and post the video. Last concept, atomic radius. What do we mean by atomic radius? Well, it depends on how it's determined, right? The neutral atom, we think of as having a radius, but we've already explained that when we're describing the electronic configuration outside the nucleus, it's a probability. We don't know exactly where it happens. So we have to estimate it depending on what type of atom it is, what type of element, as to which method we use to determine the distance between elements. Now, in general, if we know the distance between the nuclei of two atoms, then we just take half of that, and that's the radius. But it's not always that simple, because you don't necessarily know where the outer limit is. And if you have two elements like hydrogen that are bound together, they're going to be closer than they would normally be if they were separate atoms, because they bonded, which means some of their electronic density is overlapped to form the bond. Okay. So we have generally two types of radii that are recognized. For most of the periodic table, they're metals. So we can use metallic radius. And what we need to know is the distance between adjacent atoms in a solid. And we can measure that with X-ray diffraction. I haven't described X-ray diffraction yet. Okay. Oh, that comes in the second semester. Right. So just accept it for now. But it's fairly reliable. We can measure the distance between atoms in a crystal, a metallic crystal, and determine what the radius is. Covalent radius is a little iffier. 1/2 the distance between the nuclei in a homonuclear diatomic molecule. Sometimes they use X-ray, sometimes electron diffraction or neutron diffraction. Some use microwaves, combination of several, and sort of average the values. Like I said, when you form the covalent radius, the covalent radius is an estimate of the atomic radius. It's not, because there's overlapping orbital, they're actually closer than you would expect. So that's why we have to qualify it by saying covalent radius. Okay, so what are the trends? Well, we take values from several sources and average them together and get sort of an idea and build our periodic table based upon these values. And if we do, then we find that across a period from left to right, the atomic radius decreases. So that means that the electron cloud out here shrinks. And it shrinks because there are more protons in the nucleus pulling on those electrons. That shrinks the atom. That's your explanation from left to right. From top to bottom, the orbital size, the size of the atom, the atomic radius, increases because you're adding electrons into higher and higher principal quantum numbers. Remember, that's size and energy. So as you go down, they're getting bigger because you're adding to bigger orbitals. So as you go up, they should decrease in size, and as you go from left to right, they decrease. So for atomic radius, the trend is opposite from ionization and affinity. Lower left to upper right, the atomic radius decreases. And there's sort of a artist rendition. Take it for what it's worth. Which should be a larger atom? Let's see, sodium and chlorine are in the same period, so chlorine should be smaller. Oh, yeah, and sodium would be larger. How about up and down? Well, cesium is below lithium, so it should be bigger. Okay. Now, when we look at individual orbitals, which one is larger, the hydrogen 1s or the lithium 1s? Well, what that says is that 1s, the principal quantum number, speaks to size and shape. Energy and shape. No, not shape. Size. Excuse me. Energy and size is the principal quantum number. They both have the same one, but lithium is below hydrogen, so it has more protons, and it should shrink. So that would be larger. The 1s for the hydrogen is larger, which is lower energy. Well, the larger one means that the electron cloud is further from the nucleus, which means higher energy. So the lithium should be the lower energy. Okay, arrange these elements: oxygen, fluorine, and sulfur. Oxygen, fluorine, and sulfur. So oxygen's here, fluorine's here, and sulfur's there on the periodic table, according to increasing ionization energy. So lower left to upper right, we're increasing ionization energy this way and that way. So it'd be sulfur, oxygen, fluorine. Atomic size would be just the opposite. Right? Increasing would be the left to right, fluorine, oxygen, sulfur. Okay. Final thoughts. That must mean we're close to the end. Yeah, last slide. Okay. We won't have to spend a lot of time on this, just a reminder. The number of and type of valence electrons that primarily determine the atom's chemistry. So those electrons that are in the outermost shell, that's where the chemistry happens. Electron configurations can be determined from the organization of the periodic table. That is true. We know which regions are filling which orbitals, right? First two s orbitals, right 6 p orbitals, middle transition elements are d orbitals, and the lanthanides and actinides are f orbitals. certain groups in the periodic table have special names. Well, yeah, that's true. No surprise there. Basic division of the elements in the periodic table is into metals and nonmetals. Yep. Down that black line. Starts under boron and above aluminum. Yeah. And then stair steps on down. That's it. I didn't do too bad. 15 minutes. I've been known to go longer. Much longer. Okay, we'll see you next Tuesday for a review and lab. And we're going to do molar mass of an acid by titration, I think.